All right, let's dive into something huge. How do we, actually tell a computer what to do? It seems like magic, but it's not. Let's break it down.
Seriously, have you ever stopped to think about this? Your phone, your laptop, they seem so smart, right? But here's the secret. They can't think. Not at all. They're just really, really good at following orders, our orders. So, how in the world do we speak their language? Okay, so the first hurdle is a big one. It's basically a massive communication gap. The way our brains work and the way a computer thinks are on completely different planets.
And this is where it gets wild. We humans, we live in a world of big ideas, abstract thoughts, logic, creativity. But a computer, it lives in a world of on and off. That's it. Just electrical signals, a 1 or a 0. So how on earth do you get from a brilliant idea in your head to just ones and zeros?
That's where programming comes in. That's the magic. At its core, programming is just the art of writing a perfect set of instructions. It's the bridge we build to connect our world of ideas to the machine's world of simple electrical actions.
So if programming is the bridge, what's it made of? Well, it's not built with just one material. It's built in layers, using different kinds of languages. Let's start at the very bottom, right at the foundation. Right down at the very bottom, you've got machine language. This is the computer's mother tongue. It's the only thing its brain, the processor, can understand directly. And it's literally just ones and zeros. That's it. On, off, on, off.
I mean, just look at this. You see that long string of numbers? That's the word hello. Can you imagine trying to write an email, let alone a whole video game, using that? No way. It would be an absolute nightmare to write, and even worse to try and fix if you made a mistake.
Exactly. So to save our sanity, we got clever. We built on top of that foundation. We created these layers of abstraction. It's like building the first floor, then the second floor of a building. Each new layer is a language that's easier for us humans to understand. And we just have a system to translate it all back down to those ones and zeros the computer needs.
And this really shows the difference. You have low-level languages, which are super close to the metal, to the hardware itself. And then you have high-level languages, which look a lot more like English. And there's the key trade-off, right? The higher up you go, the easier it is for us to write, but the more work the computer has to do in the background to translate it all. Okay, let's make this real. Let's talk about an absolute legend in the programming world, the C language. This one changed everything.
So why was C such a game changer? Well, for one, it was portable. You could write code on one machine and it would actually run on a different one. That was huge back in the day. Plus, it was lightning fast because it got translated right down to machine code. And it was structured, meaning your code wasn't just a giant mess. That powerhouse combo is why C was used to build, well, almost everything. We're talking operating systems, the software you're using right now. So much of it has C in its DNA.
All right, so we get the languages. But what does a programmer actually do? How do you go from a thought bubble over your head to a real working app on a screen?
Well, it usually boils down to a 4-step dance. First you plan, then you write, then you translate, and finally you execute. That's the basic workflow that takes an idea from your brain to your screen. And that first step, planning, is maybe the most important one of all. You don't just start typing. No, a smart programmer first comes up with an algorithm. And an algorithm is really just a fancy word for a recipe. It's your step-by-step plan. A lot of times they'll even draw it out as a flowchart, just to make sure the logic actually works before they write a single line of code. So after all that planning, you write the code. It gets translated from your high-level language down into the computer's native ones and zeros. And then, the moment of truth, execution. The computer takes those instructions, follows them to the letter, and poof, your idea's alive. It appears on the screen just like the classic hello world that every programmer starts with.
But let's be real for a second. Does it ever work perfectly on the first try? No, not even close.
And that's because of bugs. Yep, those pesky errors. A huge part of programming is actually detective work, hunting down and squashing bugs. They come in a few flavors. You've got your simple syntax errors, which are basically just typos. A forgotten semicolon can break everything. Then you've got the sneaky ones, logic errors. This is where the program runs, but it does the completely wrong thing. Like telling a calculator that 2 + 2 = 5. And then there are runtime errors, the ones that just make the whole program crash and burn, like if you accidentally tell it to divide by 0. So when you step back and look at the whole picture, the planning, the languages, the bug hunting, you realize something important.
Programming is so much more than just typing.
And that really is the main takeaway here. It's not just about writing code. It's a creative act. It's about problem solving. It's a way of thinking, a tool that lets you take an idea, something that only exists in your mind, and make it real. Which brings us to a final question for you. Think about it. This ability to tell a machine what to do, it's kind of a modern superpower. So if you had that power, what problem would you solve first?